Okay, boys and girls, it's your lucky day today. Get to learn some more math. Today we're doing the alternating series test and the Dirichlets test, which means good test. All right, so here's a really good series to start off with. You see it's almost like the harmonic. Let's remember the harmonic one. The harmonic one is the one that everybody knows. It goes like this as n runs from 1 to infinity. So it's the sum of 1 plus a half plus a third plus a fourth and so on and so forth. Turns out that this is actually divergent. And we've shown before that this is an infinite amount. And so today we take a small little tiny variation of that. We suppose what would happen if we added an alternating sign on that. And so instead of doing sum of all the 1 over n's, we do the alternating sign. So the first one might be something like, let me just start off on a positive note. So I'm going to go with like this, n plus 1. So the first one would be negative 1 square over 1 plus negative 1 to the third over 2 plus the next one would be 3. Then it would be negative 1 to the 4th. So the top one here is 1 ahead of this one. And that would turn out to be the one I've just written. It would be 1 plus, or negative a half plus a third plus negative a fourth and so on and so forth. It's a super interesting question to see if we could add this famous alternating harmonic. It turns out to be not super easy to add, and so as usual, when these things are not easy to add, we may be able to do it by the end of today. We'll take a look at some powerful ideas to add this that in fact make it seem super easy. But for now, we're studying the different tests that we have to see whether or not a series converges or diverges. And today we're going to introduce a new one called, or a couple new ones, called the alternating series test and a Dirichlet test. In fact, the alternating series test will help us prove this. It is exactly the medicine we need to take care of this pain. So it goes like this. The alternating series test says that it's got a couple ifs and thens. If you've got a monotone sequence that's decreasing, that would be this piece right here. It's monotone and going to 0. Limit is going to 0. If you got these two key ingredients here, then if you had any kind of alternating sign here where it's plus, minus, and it could also be the other way around, minus, plus. It wouldn't be much different, but the ingredients that you need is monotone decreasing, limit going to 0, and you've got an alternating sign here. Okay, then you can just stop right there. The series converges by the alternating series test. And in fact, this is the classic example, the alternating harmonic series. First, we check that 1 over n is decreasing. That's kind of obvious because among other reasons, you could plot it here. 1, 2, 3. At 1, it's 1. At 1/2, it's 1/2. At 2, it's 1/2. At 3, it's 1/3. Clearly, this graph is going down. This is 1 over x. Another option might be to just use some sort of algebraic argument. Clearly, n plus 1 is greater than n, so therefore 1 over n plus 1 is less than 1 over n, so therefore the thing is decreasing. Every n plus 1 term is smaller than the previous term. Or you could use some sort of derivative argument. This is an alternative method to show it's decreasing. Alternative method. And of course, even a different alternative method might be just looking at the derivative. If you have f of x is equal to 1 over x, f prime of x is equal to negative 1 over x squared. This shows you that this is true for all possible values of x's, since when you square it, it wouldn't change the sign of the bottom. Even if x was negative, this would be positive. If x is positive, the square is positive. So this quotient is always negative since the numerator is negative, meaning that the first derivative is always negative, meaning that all tangent slopes are going downhill and the function is always decreasing. Okay? So any one of those arguments would work to prove that you got a monotone decreasing function. Clearly, the limit is going to 0. You can just try the plug-in method. The limit as n goes to infinity for 1 over n. Let's try the plug-in method. That would be 1 over infinity. That would give 0. Check. And so as soon as you see that you meet these two conditions, then you can just stop and say, okay, therefore this series, the alternating harmonic series, well, it wouldn't matter. If that one is convergent, the one with the extra negative would also be convergent. This one, I have to have a +1, sorry. +1. This one also converges. And then you're done. Okay. So that's how you use the alternating series test. Okay, let's see if we could do another example. Say you take this super complicated thing. The bottom one looks incredibly scary. You got a square root going on here. You got an ln here. You got an n over here with a plus. It's hard to get this out of the square root. It's be hard to do the integral test. You got some weird stuff going on here. Let's study that thing for just a second. For n and sine of n pi plus pi over 2. If n is equal to 1, this would give you sine of 3 pi over 2. If n is equal to 2, this would give you sine of 5 pi over 2. And so on and so forth. This would give you sine of 7 pi over 2. Sine curve goes like this. Sine curve goes like this. At 3 pi over 2, you're right here, so you're at -1. So this gives you -1. And then you go from here, you go pi units, that would put you over here. At that point, the sign would have gone to the top, so this would be equal to 1. 7 pi over 2. You see this thing's just oscillating. This is 3 pi over 2, 5 pi over 2, 7 pi over 2. So that 7 pi over 2 is equal to -1. And so this is -1. Take a look at this piece right here. -1, +1, -1. So really all this was just a -1 in disguise. This whole thing was just a -1 to the nth power in disguise. And so great. We got this piece right here. That's equal to this piece. Okay? Now the rest of it, we have to check that 1 over the square root of n plus ln of n is decreasing. Well, how would you show that it's decreasing? Well, super easy. N plus ln of n is clearly less than n plus 1 plus ln of n plus 1. Because all you did is add more stuff here, and you added more stuff here. Taking the ln just of a bigger number gives you a bigger number than the ln of a smaller number. Then, taking square roots preserves the radicals, or taking the radical of two sides preserves the inequality, so long as we're dealing with numbers that are less than 1 or bigger than 1. So this would be okay. We could preserve the inequality. Then flipping it, of course, does not preserve it. It flips it. So the square root of this one, which is a smaller denominator, would give you something bigger than when you have a larger denominator. And so this is, of course, n plus 1, and this is ln of n plus 1. So this shows you that this is a n is bigger than a n plus 1. So this shows you that the sequence is in fact monotone, and it's easy to see that it's decreasing. All you got to do is that the limit is equal to 0. All you do is do the plug-in method, and you'll see that the limit is 0. So the limit as n goes towards infinity of 1 over n plus ln of n. That's equal to, by the plug-in method, 1 over the square root of infinity plus infinity, which of course gives you 1 over infinity, which gives you 0. So both of these easily check off, and lo and behold, we have the powerful alternating series test being used here to conclude that this series converges. Okay, that was not hard. This was also similar thing. We're going to check first, we're going to check that this part right here, you got an alternating sign. So that tells, that's this piece right here. It switches from positive to negative, from positive to negative. Then you got to show that the square root of n all over n plus 4 is decreasing. And the reason I know it's decreasing is because this behaves a lot like, let me see here. If you look at the dominating terms, the dominating term on the top is square root of n, and the dominating term on the bottom is n. So if you were to divide out by the square root of n, which is the dominating term on the top, you get 1 over square root of n plus, well, it really, here's another way to look at it. The dominating terms on the top look like this: square root of n, forget about that 4, the dominating term is n, so this looks like 1 over the square root of n. So this guy is roughly equal to, so this one, square root of n over n plus 4, behaves a lot like 1 over the square root of n. That's what makes me think that this will be decreasing. Okay, that would be one possible argument. Maybe a better, more rigorous argument might be to use the derivative technique. So let's see if we can tackle that. F of x is equal to x divided by x plus 4. So this would become, let's look at f prime of x. This would be equal to 1/2 x to the negative 1/2 times x plus 4 minus square root of x times 1 all over x plus 4 square. The derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom square. And I'm interested in whether or not this is positive or negative. If the first derivative is negative, then you know the function is always going downhill. If the first derivative is positive, you know the function is going uphill and it's increasing. So I'm interested in the sign, whether it's positive or negative. The bottom here is always positive because you've got a square there, so I'm not even worried about the bottom. I'm more worried about whether the top is less than 0. So I'm going to have x plus 4 all over 2 times the square root of x minus the square root of x. Is that less than 0? Yes or no? I'll put here with a question mark. Well, that would be true if and only if x plus 4 is less than 2 times the square root of x is less than 0. Sorry. It's less than square root of x. I could assume that because your x's are getting big, this is a positive number. So I can multiply both sides by a positive number and not worry about the sign of the inequality. X plus 4 is less than or equal to 2 times the square root of x times the square root of x. This is true if and only if x plus 4 is less than 2x. This would be true if and only if, let's subtract x from both sides. And that would just be x, and this would always be true. This would be true if x is larger than 4, clearly. As your x is taking the place of n. So actually it may not be increasing for the first 3 items, but as soon as you take the 4th one, this will always be decreasing. And so really all you need is, who cares about the first three terms? You can move those separately and add them and see that those are finite. The series will converge if and only if the tail end converges. So we've talked about that. And so this will be decreasing, and we'll just say eventually. Or when n is larger than 4. This will be good enough for us. Okay, and we use the first derivative method to show that that was decreasing. Okay, and to show that the limit is 0 is super easy. You could just do a little L'Hopital. We'll do it here. So this is the second condition, okay? We first show that it's monotone decreasing. Next, I need to show that the limit is equal to 0. I can do that. Take the limit as n runs towards infinity, square root of n, all over n plus 4. If I try the plug-in method, that gives me infinity over infinity. So then I tried the L'Hopital method, that gives me 1 over 2 over the square root of x. I can change all this to x's, by the way. All over 1, and that's equal to 1 over the 2 square root of x. And now I'm taking the limit here as x runs towards infinity. And that's going to give us 1 over 2 times infinity, which of course is 1 over infinity, which clearly is 0. So it's pretty easy to show that that limit is 0. And that's it. Those are the two conditions you need, and you've got yourself a monotone convergence. You got convergence due to the alternate series test. Okay? Now, next one, this one's pretty much easy. Now, I wanted to do a more interesting one. No, this one. This one's slightly more interesting because let's look at this pattern here. What in the world is happening here? I'm going to make a little side table here. And I'll put n here, and I'll put cosine of n pi over 4. Now, just so we know, let me get all these pi over 4s here. This is 45 degrees. This is 90 degrees, 135. Of course, 180. And this is 45 degrees, so this is 1, square root of 2, etc., etc. This would be -1. These are just reference triangles that I'm going to use so I can calculate all this. So when n is equal to 1, for example, I would be looking at 41 times 45 degrees gives me cosine of 45 degrees. So that gives me 1 over the square root of 2. Okay? You could have done that on a calculator, but then you wouldn't even need your brain to think. Okay, for 2, that gives me, or actually you can even do it easy. You know what's even easier than that? Let's look at the graph. If that's easier. For cosine of 2, this would give me a 2 here. 2 pi over 4. That's pi over 2. That's 90 degrees. That gives you this one right here. That gives you this one right here. That gives you 0. That's 0. For the next one, 3 pi over 4. That gives you pi over 4, 3 pi over 4s. It's 135. Or said differently, 45 degrees. That gives you 135. You drop down perpendicular, you draw a reference triangle. So this ratio is -1 over square root of 2. And for the fourth one, that gives you cosine of pi. That gives you -1. For the fourth one, I'm here. Whoa. I meant to do this. I meant here, pi. At pi, cosine of pi is -1. So then we continue at 5. Now you're over here. 5 pi over 4. That's going to give you -1. So it's going to give you negative 1 over the square root of 2. For 6, that's going to give you this one. So that's going to give you 3.5 pi's. So that's going to give you here. That'll give you 0. And so on and so forth. Okay. The trouble with this series is that it's not really 1, negative 1. It's like some positive ones, then some negative ones. The next one's going to be 1 over square root of 2. That would be this one. The next one's going to be 1. The next one's going to be 1 over the square root of 2. The next one's going to be 0, and so on and so forth. So this is sort of a strange pattern. So what happens here is that you can't really, this doesn't really look like negative 1 times some other sequence. Okay? It looks a lot more complicated than that. So you really cannot say that this is equal to that, and then by alternating series test, this converges or not. It really does fail here. It's not like any of the other examples we did. So what's the conclusion? The conclusion is that we cannot apply the alternating series test. At least not in an obvious way here. So the saving grace here is the thing that we're going to talk about. The other test I would promise at the beginning of the lecture today, the Dirichlets test. The Dirichlets test says exactly the following. So you've got a monotone decreasing sequence, and that limit is going to 0. Those are the same ones that we always had for the alternating series test. But in addition, you've got this other little condition saying that the partial sum sequence of this other one sequence, SK, is bounded. All you need it to be is bounded. In other words, there's some number where these guys never go beyond that number, okay, in absolute value. As long as it's bounded, then the product of these two converges. That's the Dirichlets test. In fact, it's a generalization of the alternating series test, because on the alternating series test, this one would be, think about this. In the alternating series test, the Bn would exactly be, the Bn is equal to negative 1 to the n. That's the analogy here. And this is a generalization of it. And so if you look at the partial sum sequence of these ones, Sk for the Bn's, what do they add up to? As n goes from 1 to k. Well, you can make a little table here. You can see for k is equal to 1, what is the Sk? If k is equal to 1, that's just negative 1 to the 1. For k is equal to 2, this would be negative 1 to the 1 plus negative 1 to the 2. For 3, this would be negative 1 to the 1 plus negative 1 to the 2 plus negative 1 to the 3. For 4, it would be negative 1 to the 1 plus negative 1 squared plus negative 1 to the third plus negative 1 to the fourth. This, if you start adding these up, this one's equal to negative 1. This one's equal to 0, actually, because if you add negative 1 plus positive 1, that gives you 0. So these two are 0. So now this one's just going to give you negative 1. But this whole thing is negative 1, and all you're doing is adding a 1 here. So that's going to give you 0. So in fact, you can figure it out here, the pattern. What is Sk equal to? For 1, it's equal to negative 1. For 2, is equal to 0. For 3, is equal to negative 1. For 4, is equal to 0. So you can play this game all day long. For 5, it would be negative 1. For 6, it would be 0, etc., etc., etc. In fact, all these numbers are bounded. Negative 1, 0, negative 1, 0, negative 1. These are all bounded. Clearly is bounded in absolute value by, for example, the number 2. They never ever get past 2. And so therefore you could apply the Dirichlets test to any alternating series and see that it would converge by the Dirichlets test. This is a generalization of the alternating series test. In fact, it's bigger and better and more powerful, where the alternating series test is just one tiny example of instance of it. where the bn's are just the alternating signs. We can apply it here. We made a little chart earlier. This is going to be our bn. Our bn is going to be exactly this. Okay? Now let's see if we can show that our partial sum sequences are bounded. So first thing I'm going to do is I'm going to write a k here. And I'm going to try to find out the SKs. But before that, I'm going to try to write out a n here and the bn. So we said for n is equal to 1, that's 1 over the square root of 2. For n is equal to 2, this is 0. For n is equal to 3, that was negative 1 over square root of 2. Then it was for 4, it was equal to negative 1. For 5, it was negative 1 over the square root of 2. For 6, it was back to 0. For 7, it was equal to... See, what I'm doing is I'm following this thing. It starts off here, negative, that's this one. Then it goes to 0, then it goes to negative that. It's going like this. Then it goes to negative 1. Then it goes to negative square root of 2. Then it goes to 0. So then it goes to positive square root of 1 over square root of 2. Then it goes to 1. And then it repeats all over again. Okay? Now, for S, think about this. For K is equal to 1, all we're doing is adding one of them. For K is equal to 2, we're adding 2 of them. For K is equal to 3, we're adding 3 of them, and so on and so forth. So for 1 is equal to 1 over the square root of 2. For 2 is equal to 1 over the square root of 2. For 3 is equal to 0. For 4 is equal to, well, it's whatever I had for 3 plus the fourth one. So that would give me all 4. This would just be negative 1. For the next one is negative 1 minus 1 over the square root of 2. For the next one is the same thing. Negative 1 minus 1 over the square root of 2. You might be thinking, why is it the same thing? Well, because whatever I had for the first 5 terms, it's the same as for the 6th term. Whatever I have for the first 6 terms, because the 6th one is 0. So that's how I know that. For the 7th one, I am adding all this. And so I'm going to take whatever I had up to here and then add 1 over the square root of 2. That would kill that one. And in fact, this would just give me negative 1. For 8, that would give me 0. And you see that for 9, it would just repeat itself, and I'd go back to this one, and that one, and that one, and that one. So, so the SKs are all, in absolute value, they're all less than. I just have to figure out what's the biggest number that pops up on my radar, and in any one of these. This number is like 1 over divided by 1.7. I can see clearly that all these numbers are, for example, less than 5. And so there it is. Things never ever get past 5. And so I will have shown this part of the condition, that the partial sum sequence is bounded by 5. And in doing so, I completed all the conditions required for the Dirichlets test. And now I can safely declare this series, it converges by the Dirichlets test. Okay? And that's it. Those are the 2 tests that we're learning today. The Dirichlets test and the alternating series test. By the way, the proofs of these are super, super interesting. I highly recommend that you go on and try to find a proof and try to understand it. To finish lecture off today, I thought we could go back to the problem we started off with, which was the famous alternating series test. We've already shown that it converges using the alternating series test, but I'm wondering if we could actually add it. And for that, we're going back to the motive for the entire chapter, which was the connection between these 2 worlds there. Where on the one world, we have the world of polynomials, such as 1 over 1 minus x, and the other world, or these things that are not polynomials, and then polynomials, 1 plus x squared plus x to the third, and so on and so forth. this crazy world, right? And so I want to go back to that and see if we can actually not just prove that this converges, but actually figure out what the hell does it converge to? How do you add this crazy infinitely long list of fractions, 1 minus a half plus a third minus a fourth plus a fifth, all the way to infinity? The audacity of humans to think that they can add all the way to infinity, it's mind-boggling. But I think we can do it. We have enough ideas in our arsenal to make some decent damage on this idea. Let's see. We know that 1 over 1 minus x is equal to 1 plus x squared plus x to the third plus x to the fourth. Under favorable conditions, that's called a geometric series. Favorable meaning absolute value of x is less than 1. We also know that we could replace x with negative x. That would mean that x plus x is equal to 1 minus x plus x squared minus x to the third plus x to the fourth, dot, 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 dot. We also know that we could go on and we slap some integrals on these with respect to x, and that would tell us that ln of 1 plus x would be equal to x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4 plus x to the 5 over 5, and so on and so forth. And now we go on and we do something amazing, something crazy, something that takes a lot of guts, something bold. What if we substitute here, x equals 1. If we go on and substitute x equals 1, on the left side I'd get that ln of 1 plus 1, that would be equal to 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5, etc., etc., etc. So in fact, I would get that ln of 2 is equal to 1 minus 1 half plus 1 third minus 1 fourth plus 1 fifth minus 1 sixth, and so on and so forth, all the way to infinity until the sun stops shining, all the way to infinity. And lo and behold, I get the precise number that infinite series is equal to. It's equal to ln2. And that, my friends, feels good when you can prove that this is equal to ln of 2. There are some little details that are left off, like, for example, how do you know that you can just go on and plug 1s in there? There were some restrictions. This shouldn't be bigger. The x's shouldn't be bigger than 1. So some minor little things that are still left here to prove, but overall, I think the idea is so amazing. All right, we're going to call this a day. Don't forget to subscribe. We'll see you guys next time.